In February 2025, physicists at the University of Surrey published something the field has been quietly dreading for decades. The mathematics they worked through showed without exception that time's equations run just as cleanly backward as forward. Not almost, not approximately. Exactly, two arrows of time emerging simultaneously from the same quantum system. And what terrifies them is not the math. What terrifies them is what the math is describing. A direction of time they have been trained not to discuss. That silence ends tonight. Think about the last time you watched a fire burn. The wood consumed itself in a direction you recognized immediately. You did not expect the smoke to gather back into the log. You did not expect the ash to reassemble into bark. You did not need anyone to explain which way the fire was running. Your entire nervous system knew. It felt obvious. It felt like a law so deeply written into reality that questioning it would be the same as questioning whether objects fall down when you drop them. Time moves forward, things age, disorder increases, the past is sealed, the future is open. These are not beliefs you adopted, they are convictions your cells carry. And yet, every fundamental law of physics disagrees with you, not partially, not in some narrow technical footnote. Across every framework from Newton in the 17th century to quantum field theory in the 21st, the equations that describe physical reality run with perfect indifference in either direction through time. Forward, backward, it makes no difference to the mathematics. The universe's own description of itself contains no preference, no arrow, no insistence that one direction is different from the other. This is not a philosophical puzzle. It is not the kind of uncertainty that philosophers enjoy arguing over in comfortable chairs while the hard sciences get on with real work. This is a specific, technical, experimentally verified mismatch between what the laws of physics say and what every human being who has ever lived has felt to be the deepest certainty about existence. The mismatch has been sitting in physics textbooks for 150 years. It has been called the arrow of time problem. And the closer physicists look at it with modern instruments and modern mathematics, the stranger the answer becomes, because the answer is not that the laws of physics are missing something. The answer may be that time genuinely has two directions, and the universe is running both of them simultaneously, and the version of time you experience is only half the story. That is the thing physicists are terrified to discuss, not because it is unscientific, not because the evidence does not support it, but because fully discussing it means confronting implications that even the most rigorous scientific framework in history has not yet found a comfortable way to frame. It means taking seriously the possibility that on the other side of the moment we call the Big Bang, time has been running in the opposite direction for just as long as it has been running in hours, that somewhere beyond what any telescope can reach, a universe entirely symmetric to our own is aging in reverse, that the laws of physics faithfully applied do not produce one cosmos, but two, twins, moving apart from a single instant in opposite temporal directions. It means asking whether the direction of time you experience is a law of nature or simply the neighborhood of the universe you happen to inhabit. Before we go anywhere near that territory, though, we have to understand why the problem is so severe. Because it is tempting, hearing that physics is time-symmetric, to dismiss it as a technicality. Surely the real world shows obvious time asymmetry, you might think. Eggs break, but do not unbreak. People age, but do not unage. Coffee cools, but does not spontaneously reheat. These are not subtle laboratory effects. They are the most visible features of everyday experience. So how can physics be claiming that its laws show no preference for one time direction over another? What is the gap between the equations and the experience, and where does it come from? The gap has a name. It was identified with uncomfortable clarity by the Austrian physicist Ludwig Boltzmann in the 1870s, and the clarity has never quite faded from view since, even when generations of physicists have tried to change the subject. Boltzmann was working on the statistical mechanics of gases, trying to understand why thermodynamic processes have the directional quality they do. He succeeded in deriving the second law of thermodynamics from first principles, which was a genuine achievement of enormous significance, and in doing so he accidentally showed something nobody wanted to be true. The second law, the law that says entropy always increases, the law that seems to be the engine of time's arrow, is not actually a law in the deepest sense. It is a statement about probability. And probability, unlike a genuine law, has an asterisk. Boltzmann's equation is carved on his tombstone in Vienna. S equals k times the natural logarithm of W. In that compressed notation, S is entropy, k is a tiny constant that bridges the macroscopic and microscopic worlds, and W is the number of microscopic configurations of a system that are consistent with its observable macroscopic state. When you have a gas of molecules in a box, the temperature and pressure you measure are macroscopic properties, but those properties are compatible with an enormous number of different possible arrangements of individual molecules. The key insight is that higher entropy states are consistent with many more such arrangements than lower entropy states. There are vastly more ways for a gas to be evenly distributed throughout a box than there are for all the molecules to be crammed into one corner. So when you start with the gas crammed into one corner and let it evolve according to the reversible microscopic laws of physics, it almost certainly ends up spreading out. Because there are so many more spread out arrangements to land in, it is not compelled to spread by any force. It is overwhelmingly likely to spread because spread is where almost all the available configurations are. This is brilliant. This is also, when you stare at it long enough, terrifying. Because here is what it means. Entropy does not increase because a law says it must. Entropy increases because high entropy states are statistically overwhelmingly more probable than low entropy states. The second law is not a command issued by the universe. It is a report on where the odds lie. And here is where the arrow of time begins to wobble. Because statistical probability is symmetric in time. If it is extraordinarily unlikely that a gas of molecules will spontaneously arrange themselves into one corner of a box starting from an evenly distributed state, it is equally unlikely that they will do so in reverse. The probabilistic argument gives you an arrow pointing away from low entropy states in both temporal directions, not just into the future, into the past as well. If entropy tends to increase going forward in time, then by the same logic, it also tends to increase going backward in time, which would mean that if you started at any given moment and asked what the past was probably like, the answer statistical mechanics gives you without any additional information is that the past was probably higher entropy than the present, not lower, higher, more disordered, not less. But that is precisely backward from what we observe. We observe a past that was very low entropy. We observe a universe that started some 13.8 billion years ago in a state of extraordinary, implausibly precise order. The cosmic microwave background, the faint thermal glow that fills the sky at a temperature of 2.725 Kelvin, is the most nearly perfect blackbody spectrum ever measured in nature, deviating from the theoretical ideal by less than 50 parts per million. The early universe was smoothed to 1 part in 100,000. That is not what you expect from a high-entropy state. That is what you expect from an extraordinarily low-entropy state, a state so precisely ordered that the mathematician Roger Penrose, after attempting to calculate the probability of the universe starting in such a configuration, wrote down a number that has become one of the most staggering in all of science. The odds against the universe beginning in the state it began in, selected at random from all possible initial configurations, are approximately 1 in 10 raised to the power of 10 raised to the power of 123. This is a number so large that the number of atoms in the observable universe, roughly 10 to the 80th power, looks like a rounding error in comparison. This extraordinary initial condition is what the philosopher of physics David Albert calls the past hypothesis, and it is precisely this hypothesis, the stipulation, that the universe began in an exceptional state of very low entropy, that does the actual work of giving time its arrow. The laws of physics are symmetric. The past hypothesis is not symmetric. It picks out one end of the universe's history as special. And from that asymmetric starting point, entropy has been climbing toward equilibrium ever since. And that climb is what we call the flow of time. But here is what the past hypothesis cannot do. It cannot explain itself. It cannot tell you why the universe began in that extraordinarily improbable state. It is not derived from the laws of physics. It is assumed in addition to them, inserted as a boundary condition rather than derived as a consequence. The laws describe how the universe evolves. The past hypothesis describes where it started, and the question of why it started there, in that specific, implausibly ordered configuration, is the question that every serious attempt to explain the arrow of time eventually runs into and cannot get around. Some physicists say the past hypothesis is simply brute fact. The universe had to start somewhere, and it started there, and that is the end of the matter. Others find this deeply unsatisfying. If the initial condition is the most improbable configuration in the universe's history, if it is the configuration least likely to be produced by random chance, then calling it brute fact feels like giving up. It feels like saying the universe began with a miracle and calling that a scientific explanation. And the physicists who find this unsatisfying have been searching with increasing urgency for a different answer. An answer that explains not just how time flows forward from the initial condition, but why the initial condition was what it was. Why, if the laws of physics are symmetric, the universe began at one extreme end of the entropy spectrum rather than somewhere in the vast middle. The search for that answer is what has led physicists, step by careful step, to a possibility that most of them have been reluctant to state explicitly. The possibility that the universe's extreme low entropy initial state is not the start of a single arrow of time, but the pivot point of two. That the Big Bang was not the beginning of time in one direction, but the minimum complexity moment from which time flows outward in both. That there is, beyond our observational horizon, a second cosmos aging in the direction we call the past, and that the reason our universe began in such an improbably ordered state is that ordered states are what you get when you are sitting at the midpoint of a time-symmetric universe, not at its beginning. Before we reach that conclusion, though, we have to understand another piece of the puzzle, one that comes not from thermodynamics but from particle physics, one that should, by rights, have settled the question of time's fundamental symmetry long ago, but instead complicated it in a way that still has not been fully absorbed. It has to do with a class of unstable particles and a minute violation of a symmetry so basic that its discovery in 1964 shook the foundations of physics. It is the discovery that time reversal symmetry at the deepest level of the microscopic laws is not perfectly exact after all. In 1964, James Cronin and Val Fitch were conducting experiments at Brookhaven National Laboratory in New York using particles called kaons. Kaons are unstable particles containing one strange quark, and they come in pairs that are related by a symmetry called CP-symmetry, which is a combination of charge conjugation, swapping particles for antiparticles, and parity, reflecting space as if in a mirror. The standard expectation at the time was that the laws of physics obeyed CP symmetry perfectly, meaning that if you replaced every particle with its antiparticle and reflected space, the physics would look identical. Cronin and Fitch found that it did not. The neutral kaon system violated CP symmetry by a tiny but unmistakable amount. This was so unexpected that Cronin and Fitch were awarded the Nobel Prize in Physics in 1980 for the discovery. What does CP violation have to do with time? The answer comes from a theorem called the CPT theorem, which is one of the most deeply established results in all of quantum field theory. The CPT theorem states that any Lorentz invariant quantum field theory, which is the framework that underlies all of particle physics, must be symmetric under the combined operation of charge conjugation, parity transformation, and time reversal applied simultaneously. This is CPT symmetry, not each one separately but all three together. And the CPT theorem is not an assumption. It is a mathematical consequence of the structure of quantum field theory that follows from very general assumptions about locality and Lorentz invariance. It is essentially impossible to violate it without destroying the entire framework. The implication of CP violation for time reversal follows directly. If CPT symmetry holds, which it does, and if CP symmetry is violated, which it is, then T symmetry, time reversal symmetry alone, must also be violated by exactly the same amount in the same system, otherwise the three would not balance. CP violation, in other words, entails T violation, a genuine, measured, physically real asymmetry between forward and backward time in the laws of physics themselves, not a statistical asymmetry arising from initial conditions, a lawful asymmetry built into the fundamental interactions. This was confirmed experimentally with more precision as the decades passed. The Baybar experiment at SLAC in California, which studied the decays of particles called B mesons, reported a direct measurement of time reversal violation in 2012. Not CP violation being used to infer T violation, but T violation itself, measured directly in the decays of real particles in a real detector. The result was unambiguous. The forward and backward versions of certain B meson decays happen at different rates. Time is not perfectly symmetric at the level of fundamental particle interactions. The laws themselves, at their most microscopic, know which direction is forward, and yet this makes the arrow of time problem stranger, not simpler. Because the T violation that has been measured is tiny. It is on the order of 1 part in 1,000 in the weak force interactions where it appears. The second law of thermodynamics operates at the level of certainty rather than 1 part in 1,000. The overwhelming directionality of macroscopic time, the shattering of eggs, the cooling of coffee, the aging of organisms cannot be explained by a T violation that's small acting on individual particles. These phenomena require the statistical argument. They require the past hypothesis. The T violation in particle physics is a hint. It is a whisper. It is not an explanation. What T violation tells us is that the laws of physics are not perfectly symmetric in time. They have a slight preference, a tiny, measured, real preference for one direction over the other. This preference is not large enough to explain the macroscopic arrow on its own, but it does mean that the question of time's fundamental directionality is not purely a matter of initial conditions and statistics. There is something in the laws themselves that is not perfectly indifferent, and that something, however small, has implications for what a time-symmetric universe would actually look like. Because if the laws prefer one direction by even a little, then a perfectly CPT-symmetric universe, one in which a mirror cosmos runs backward in time on the other side of the Big Bang, would not be an exact copy. It would be a CPT image, a universe in which every particle is replaced by its antiparticle, every spatial coordinate is reflected, and time runs in the opposite direction. Not a perfect mirror, a CPT mirror. That is exactly the kind of universe that a group of physicists at the Perimeter Institute for Theoretical Physics in Canada proposed in 2018. Latham Boyle, Kieran Finn, and Neil Turok published a paper in Physical Review Letters with a simple and radical proposition. The universe as a whole does not violate CPT symmetry. Our universe, in which time runs forward, antimatter is rare, and space has its familiar geometry, is paired with an anti-universe emerging from the same Big Bang event in which time runs backward, matter is rare, and antimatter is the normal constituent of matter. Together they form a CPT-symmetric pair. The Big Bang is not the beginning of one universe. It is the point of contact between two, moving in opposite temporal directions, each one the CPT image of the other. The beauty of this proposal is not merely aesthetic, though the elegance is real. The proposal explains things that have otherwise required additional exotic ingredients. It explains the asymmetry between matter and antimatter in our universe. If our universe is the matter half of a CPT pair, the anti-universe naturally contains the balancing antimatter. No additional mechanism is needed. The asymmetry we observe is not a violation of CPT at the cosmological level. It is our local half of a globally symmetric pair. The proposal also provides a natural candidate for dark matter. In a CPT-symmetric universe, certain right-handed neutrinos that are otherwise sterile, meaning they interact only through gravity, become the natural dark matter candidate. Their abundance can be calculated from first principles, and the mass that matches the observed dark matter density comes out at approximately 480 million billion electron volts. A specific, testable prediction arising from symmetry rather than invented to fit the data. The anti-universe in this picture is not a place you can visit. The CPT partner exists on the other side of the Big Bang, in what was, from our perspective, before the beginning. Time and space flow continuously across the Big Bang singularity in this model. There is no hard edge, no boundary beyond which physics fails. The singularity is the contact point between two expanding, cooling, structure-forming universes, one of which we inhabit, the other of which is, in every sense that matters for physics, as real as ours. We cannot see it because there is no path from our side of the singularity to the other side that does not require crossing the full energy density of the Big Bang, which is precisely what our telescopes cannot penetrate. But the laws of physics, faithfully applied, say it is there. Boyle and Turok's proposal arrived in journals already warmed by a related set of ideas from Julian Barbour, a British physicist based at the University of Oxford, who has been one of the most serious and persistent thinkers about time in the history of modern physics. Barbour's work, developed with his collaborators Tim Kozlowski and Flavio Mercati, and formally published in Physical Review Letters in October 2014, arrives at a similar conclusion through a different route. They called their key result the identification of a gravitational arrow of time, but its implications reach much further than that label suggests. Barbour's starting point is a philosophical position he has held for decades. Time, he argues, is not a fundamental ingredient of physics. It is something that physics produces. The question is what produces it. And his answer, refined through years of working with Newtonian particle systems, is that the direction of time is produced by the growth of what he calls complexity. Not entropy in the usual thermodynamic sense, but a different measure, one that captures how structured and differentiated the universe's content is. And the crucial insight is that for any collection of gravitating particles starting in a configuration of minimal complexity, the natural evolution of those particles under gravity produces increasing complexity in both temporal directions simultaneously. The universe, as Barbour describes it, looks, from the point of view of a physicist outside it, like a movie that starts in the middle. At the central moment, what Barbour named the Janus point, after the two-faced Roman god of beginnings, the universe is at its simplest, most uniform, most disordered configuration. From that point, the gravitational dynamics naturally drive increasing structure in both directions. Stars form, galaxies organize, complexity grows. And crucially, it grows in both directions from the Janus point. An observer living in one direction would experience time as flowing away from the Janus point toward increasing complexity. An observer living in the other direction would experience exactly the same thing. Both would have a clear past and a clear future. Both would be correct about the direction of their experienced time. and neither would have any way of knowing that on the other side of the Janus point, an equally valid arrow of time is running in what they would call the wrong direction. Barber's own description of this from his 2020 book, The Janus Point, is quietly devastating in its implications. He writes, effectively, that if the theory is right, there is another universe on the other side of the Big Bang in which the direction of experience of time is opposite to ours, not a theoretical possibility, a consequence of applying the laws of Newtonian gravity to a sufficiently large collection of particles and following them without prejudice to see what they do. What they do is produce two arrows, not one, with the Janus point sits between them like the pivot of a scale. Our past is their future. Our future is their past. And the universe as a whole has no arrow at all. Only local regions have arrows, and those arrows point away from the place of minimum complexity in opposite directions. Barber was careful to acknowledge the limitations of his model. It used a simplified picture of gravity and did not incorporate general relativity or quantum mechanics. These are not small omissions. The universe does not actually run on Newtonian gravity. But the pattern he identified, the emergence of two opposing arrows from a single point of minimal complexity, is sufficiently robust in simpler models that he and others believe it will survive the transition to a more complete physical theory. Sean Carroll at the California Institute of Technology and Alan Guth at the Massachusetts Institute of Technology, working independently with different particle models, found the same pattern. Even without gravity, even with particles interacting through nothing but their positions, two arrows emerged from the configuration of minimum spread. The Janus point appears to be a feature of physics at a more general level than the specific model used to find it. Now, it is worth pausing here and acknowledging a set of objections that serious physicists have raised, because this is not a story where the evidence is settled and only the interpretation remains in doubt. The Janus point model has been criticized for relying on initial conditions that are themselves unlikely. If you place a finite collection of particles in an infinite universe in a small initial volume, of course the particles will spread out over time in both directions. The question is whether this actually explains the observed arrow of time in our specific universe, or whether it simply demonstrates that two arrows can emerge from some initial conditions without explaining why our initial conditions were what they were. This is a real tension in the program. Barber's proposal has enthusiastic supporters among physicists who find it beautiful and provocative, and it has critics who find it elegant but ultimately circular, moving the explanandum rather than eliminating it. What is not in dispute is the mathematics. The two-arrow structure is real in the models where it has been found. The question is whether it reflects something true about the actual cosmos, and that question will be answered, if it can be answered, by observations that have not yet been made, and possibly by theoretical developments that have not yet been achieved. But there is another line of evidence for something deeply strange about time's arrow, one that is experimental rather than theoretical, and one that has been accumulating quietly in physics laboratories for years. This evidence does not come from the cosmic scale, it comes from the smallest scales possible, from individual atoms, individual qubits, individual particles, manipulated in quantum computers. And what it shows is that at the quantum level, the arrow of time is not only reversible in principle, it has been reversed in practice. The first dramatic demonstration of this came in 2019 from a group of researchers at the Moscow Institute of Physics and Technology. They published a paper in Scientific Reports titled Arrow of Time and Its Reversal on the IBM Quantum Computer. The paper describes a procedure in which they took a quantum system, a collection of qubits on IBM's publicly accessible quantum computing platform, and deliberately reversed the direction of its temporal evolution. They prepared a qubit in a localized, organized state, watched it evolve forward in time, spreading out and becoming disordered in the quantum equivalent of gas, expanding to fill a box. and then applied a specially designed quantum algorithm that reversed the evolution. The qubit returned to its initial organized state. Entropy, by any reasonable quantum measure, decreased. The arrow of time ran backward. This is not time travel in any dramatic or science-fictional sense. Nothing moved through time. What moved was the quantum state of a tiny system, and it moved in the direction physicists call toward the past. For 2 qubits, this worked with 85% fidelity. For 3 qubits, it worked 50% of the time. The success rate decreases as the system grows because engineering the precise reversal becomes exponentially harder. For a macroscopic system with something like 10 to the 23 particles, the required precision would be so astronomical that it would never occur spontaneously in the age of the universe. This is why you have never seen a shattered glass reassemble. Not because it is forbidden, because it is improbable beyond any conceivable calculation. But the Moscow team's experiment shows something important. The laws governing the quantum evolution of those qubits contained no prohibition on running backward. The forward arrow was not law, the backward arrow was not forbidden. Both directions were equally available to the mathematics. All that the IBM quantum computer did was supply the extraordinarily precise engineering that nature would never randomly supply on its own. The arrow of time in that system was reversed, cleanly and measurably, and the universe continued to exist. In 2019, a separate group of researchers, led by the physicist Roberto Serra at the Federal University of ABC in Brazil, performed a different but equally remarkable experiment. They took 2 quantum particles and arranged them so that they were correlated in a specific way, not quite entangled in the full quantum mechanical sense, but sharing information in a way that gave them a kind of quantum memory of each other. Then they allowed heat to flow between the particles. What they found was that heat flowed from the cold particle to the hot one, spontaneously, without any external intervention, in violation of what the second law of thermodynamics predicts for classical systems. The arrow of time for those correlated particles ran backward. The direction of heat flow reversed. Warmth went from cold to hot. This was not a violation of conservation of energy. The total energy was conserved. What changed was the entropy. It decreased in a way the classical second law says it should not. The quantum correlations between the particles provided what physicist David Jennings of the University of Oxford, commenting on the experiment, called order in the form of correlations, which could be consumed to drive heat to flow in reverse. The correlations were a resource. They were fuel for a thermodynamic engine that ran in the wrong direction. And the existence of this effect means that the arrow of time for quantum systems with the right kinds of correlations is not fixed. It is thermodynamically reversible under conditions that quantum mechanics permits, and classical physics does not. Erich Lutz, a theoretical physicist at the University of Erlangen-Nuremberg, who was part of Serra's group, said it plainly. The arrow of time is not an absolute concept, but a relative concept. That sentence is worth reading again. Not absolute, relative. Relative to what? Relative to the correlations present in the system, relative to the quantum state, relative to the specific physical situation the particles find themselves in. This is not a fringe position. This is a statement by a physicist at a major research university about a result published in a peer-reviewed journal and subsequently verified by independent groups. And then, in February 2025, came the University of Surrey result. Thomas Guff, a postdoctoral researcher, led calculations examining what happens to the time reversal properties of open quantum systems, which are quantum systems that interact with an environment rather than being perfectly isolated. This is the more realistic case. Almost nothing in the physical world is perfectly isolated from its environment. When quantum systems interact with their surroundings, they become entangled with them and their evolution changes. The standard approach in physics is to trace out the environmental degrees of freedom, averaging over all the things the environment is doing, and describe just the system of interest. The resulting equation for the system's evolution has a component called the memory kernel, which encodes how the system's past interactions with the environment affect its current behavior. What Guff found, working through the mathematics carefully, was that the memory kernel is symmetric in time. The equations governing the system's evolution behave exactly the same way whether time is running forward or backward, not approximately, not under certain conditions, exactly. And there is a further subtlety. Hidden in the equations is a factor that is time discontinuous, which means it has a different value on either side of a particular moment. This discontinuous factor was so unexpected, so unusual in a physics equation, that Guff described it as very surprising to see it pop up so naturally. But it is precisely this discontinuous factor that keeps the time symmetry intact. The math was protecting its own symmetry in a way that even the researchers had not anticipated. The paper's lead author, Dr. Andrea Rocco, described it in terms that should resonate from everything we have been discussing. The equations still behaved the same way whether the system was moving forward or backward in time. Mathematical evidence derived from the equations that govern quantum systems interacting with the world around them that the time reversal symmetry of those equations is preserved even in realistic, open, environmentally coupled quantum systems. Two arrows of time, the paper's title concluded, emerging from the quantum realm. At this point, you might be thinking that all of this, as remarkable as it is, can be reconciled with ordinary experience. Quantum systems are weird. Everyone knows quantum systems are weird. The fact that quantum particles can violate the second law of thermodynamics under special correlated conditions does not mean that coffee mugs spontaneously reassemble. The fact that IBM's quantum computer could reverse a qubit's time evolution does not mean that broken windows unshatter. The quantum world and the macroscopic world play by different rules. The strangeness of quantum mechanics does not leak up to the scale of everyday experience. So perhaps none of this is as threatening to ordinary time as it seems. But here is the problem with that comfortable response. The macroscopic world is made of quantum particles. There is no line in the laws of physics where quantum mechanics stops applying and classical physics starts being the real story. The classical world is an approximation to the quantum world, a very good approximation, extraordinarily reliable at the scales of human experience, but an approximation nonetheless. And the question of why the quantum world's time symmetry does not manifest in the macroscopic world is precisely the question that has never been answered to anyone's full satisfaction. The standard answer is decoherence, the process by which quantum systems interact with their environment and lose their quantum coherence, becoming effectively classical. Decoherence is real, it is well measured, it does explain why macroscopic objects do not show quantum superposition in their behavior, but decoherence does not break time reversal symmetry. Decoherence is itself a time-symmetric process in the fundamental equations. The apparently irreversible production of classical behavior through decoherence is, at the level of the underlying equations, just as reversible as any other quantum process. The apparent irreversibility is, again, statistical. It is overwhelmingly unlikely that a decohered macroscopic system will spontaneously recohere. But unlikely is not impossible, and the equations that describe decoherence contain no built-in preference for which direction time flows. This means that the arrow of time, all the way up from the quantum level to the cosmic level, is a feature of initial conditions and statistics, not of law. And that means, as we have now seen from multiple independent directions, that there is nothing preventing a second arrow of time from existing. Nothing in the laws says there can only be one. Nothing in the mathematics prohibits the symmetric structure that Barber and Carroll and Turok and others have found when they apply the same laws to larger systems or to the universe as a whole. The second direction is not forbidden. It may be inevitable. It may be from the perspective of the universe's own mathematical structure, just as real as the direction we experience. Now we need to go somewhere that most discussions of time's arrow never quite reach. We need to go to the place where the question of time's direction becomes not just cosmological, but existential, because there is a sense in which the second direction of time is not merely a feature of distant cosmology or exotic particle physics. There is a sense in which it is present right here, embedded in the structure of the universe we already inhabit, detectable not by looking billions of years into the past or hunting for mirror universes on the other side of the Big Bang, but by looking at what the laws of physics say about the present structure of space-time. In 1905, Albert Einstein published the special theory of relativity. Among its many consequences was one that Hermann Minkowski, Einstein's former teacher, recognized before Einstein himself did and formalized in a lecture in 1908 that has been called one of the most consequential in the history of physics. What Minkowski showed was that the three dimensions of space and the one dimension of time are not separate things. They are components of a single, four-dimensional geometric structure he called space-time. And in space-time, the natural mathematical object is not a three-dimensional snapshot at an instant, but a four-dimensional manifold containing all events at all times. In this framework, which is the framework that general relativity and every fundamental theory of physics since has been built on, time is a dimension, not a special, privileged, uniquely real dimension. A dimension among the four related to the spatial dimensions by the speed of light, distinguished by a sign difference in the metric that determines distances, but fundamentally a coordinate in a geometric structure that exists all at once. The past is not gone. It is at different coordinates. The future is not absent. It is at other coordinates. The distinction between past, present, and future that feels so absolute from the inside is, in the geometry of space-time, an observer-dependent feature rather than a fundamental one. Two observers moving relative to each other will disagree about which events are happening simultaneously, about which events are in the past and which in the future, for events sufficiently separated in space. There is no universal now. There is only the local now of each observer, defined by their particular trajectory through the four-dimensional manifold. This is what physicists call the block universe. The view that all of space-time, past, present, and future exists as a complete four-dimensional structure, with no part of it more or less real than any other. Einstein accepted this view later in his life, explicitly and without reservation. When his friend Michel Besso died in March of 1955, Einstein wrote to Besso's family that Besso had departed from this strange world a little before him, and then wrote the sentence that has followed this discussion of time wherever it has appeared since. For those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. Einstein died 3 weeks later. He had spent the last decades of his life in a framework of space-time that made every moment as permanent as every other. His past was embedded there. Besso's past was embedded there. The moment of his writing was embedded there. None of these were more or less real than any other point in the four-dimensional manifold. The word gone in the block universe has no meaning. The past does not go anywhere. It continues to exist at its coordinates, inaccessible not because it was erased, but because the only direction any observer can travel through space-time is along what general relativity calls a time-like path. You cannot travel to the past because the geometry constrains you to move forward along your world line, not because the past ceased to exist. Now here is the piece that connects the block universe to everything else we have been discussing. In the block universe, the direction of your world line through space-time is not prescribed by any law. Laws govern how physical systems evolve. They determine the shape of world lines given initial conditions. but the choice of which direction you call forward in time, which temporal direction is the future, and which is the past, is in the block universe precisely the choice that the laws of physics do not make for you. The geometry contains both directions equally. The laws are symmetric. The past and the future are both there as coordinates in the manifold, equally real, equally populated with events. What determines the direction you call forward is not a law. It is the combination of two things. First, the initial condition. You started near the Janus point in the low entropy early universe, and you have been evolving toward higher entropy configurations ever since, and the direction you call forward is the direction in which entropy increases in your local environment. Second, the fact that your memory and your perception are thermodynamic processes that record information in the direction of increasing entropy. You remember what physicists call the past, because your memory accumulated records in the direction your thermodynamic situation allowed. You anticipate the future because your predictive models are calibrated to extrapolate in the same direction. But none of this is a law. It is all a consequence of where you sit on the entropy landscape of a particular universe. In a different universe, one that started at the same Janus point but whose entropy increases in the other direction, as seen from our coordinate system, every observer would have the same experiences of memory and anticipation. They would remember their past and anticipate their future exactly as we do. But what they call their past, the low complexity configuration they evolved from, is what we call the Big Bang. And what they call their future, the high complexity configurations they are evolving toward, is the universe running backward through our history from our perspective. They are real. Their time is real. Their direction of experience is as valid as ours. And neither of us can visit the other, not because one side's time is wrong, but because neither of us can cross the Janus point. We are both evolving away from it as far as local physics is concerned. This is the picture that physicists find most difficult to discuss, not because they find it implausible, but because it requires them to say out loud that there is no privileged direction of time at the cosmological level, that the universe does not have an arrow, that arrows are local, that the sense of time flowing forward, which feels more immediate and more certain than almost any other fact about reality, is not a report on the structure of the cosmos, but a description of where you happen to be sitting in a much larger, much more symmetric structure. That is not a comfortable thing to say. It lands differently than other cosmological facts. When a physicist tells you that the universe began in an extremely hot, dense state, or that most of the matter in the cosmos is dark matter that does not interact electromagnetically, or that the universe is currently undergoing an accelerating expansion driven by dark energy. These are surprising facts, but they do not destabilize the listener's relationship to their own experience. They describe things that are far away or invisible or operating on scales that do not touch daily life. But when a physicist tells you that the direction of time you experience is not a fundamental feature of the universe, that it is a local consequence of where you sit on the entropy landscape, that an equally valid arrow is running in the other direction on the other side of the Big Bang, this does not feel like an abstract fact about the cosmos. It feels like a claim about the most intimate feature of what it means to be you. It feels personal in a way that dark matter does not. And the reason physicists have been reluctant to discuss it is partly the personal weight of the claim and partly the incompleteness of the picture. Because saying that time has two directions raises more questions than it answers. It raises the question of what, exactly, is on the other side. Is there life there? Is there complexity? Is there something it is like to be an observer in the mirror universe, experiencing time in what we would call the backward direction? The laws of physics, as currently understood, cannot answer this. They can say that the mirror universe is governed by the same laws. They can say that if those laws permit the formation of stars and planets and chemistry, then the mirror universe will form stars and planets and chemistry. They cannot say whether conscious experience arises in that universe or whether it has any relationship to consciousness in ours. The hard problem of consciousness, the question of why any physical process gives rise to subjective experience, remains as unsolved on the mirror side as it is on ours. What the laws can say is that the matter content of the mirror universe, if the CPT model is right, consists primarily of antimatter rather than matter. This is a consequence of the CPT transformation that connects the two sides. Antimatter, from the perspective of particle physics, behaves almost identically to matter except for its opposite charge. The chemistry of antimatter atoms, made of positrons and antiprotons, is governed by exactly the same quantum mechanical rules as the chemistry of ordinary atoms. The periodic table of antimatter is the same as the periodic table of matter. Organic chemistry with antimatter, organic molecules, obeys the same rules as organic chemistry with ordinary molecules. There is nothing in the laws of physics that prevents complex structures, including potentially living systems, from forming on the antimatter side. The laws permit it. Whether it happens depends on the specific history of that universe, which is governed by the same equations as ours and which, by the symmetry of the CPT model, should produce similarly complex structures. This is one of the places where the discussion becomes genuinely uncomfortable and where physicists sometimes change the subject. Because if the CPT-symmetric model is right, and if the mirror universe contains observers, then there are conscious beings in that universe experiencing time in the opposite direction from us. This is not a claim about what they can experience or whether their experience is valid. It is a claim about orientation. From their perspective, what we call the future is their past. From their perspective, what we call increasing entropy is decreasing entropy from our side. They remember a universe that we have not yet reached, and they anticipate a universe that we have already left. And they would have no more way of knowing about our existence than we have of knowing about theirs. The Boyle-Finn-Turok paper addresses this with care. It notes that quantum uncertainty means the universe and anti-universe are not exact mirror images of each other. The CPT transformation is applied at the level of the overall structure, not at the level of every individual quantum event. The individual histories of the two universes diverge due to quantum randomness, which is why the existence of the anti-universe does not eliminate free will or reduce human choices to the status of echoes of events on the other side. The two universes are related by symmetry, but they are not identical. They are related the way the left hand and the right hand are related. Same structure, same laws, but not superimposable on each other. We need to go one level deeper still, because there is an aspect of the problem of time's arrow that goes beyond the thermodynamic, beyond the cosmological, beyond even the CPT-symmetric universe. There is a level at which the question of time's direction becomes the question of whether time exists at all. This is the level of quantum gravity, the frontier where the two most successful theories in the history of physics collide and produce something neither was designed to handle. This is where the problem of time's direction becomes what physicists call, with a technical precision that carries more philosophical weight than any other term in the field, the problem of time. General relativity, Einstein's description of gravity, treats space-time as a dynamic, four-dimensional geometric structure. Matter and energy curve space-time. The curvature of space-time tells matter and energy how to move. There is no fixed background, no external stage on which the drama of physics is performed. The stage is part of the drama. Space-time is not a container in which the universe exists. It is the universe. And in general relativity, time is one of the four dimensions of this dynamic geometry, which means time itself is dynamic. It is part of what the theory is solving for. There is no external time against which the evolution of space-time is measured. Quantum mechanics, the description of matter at the smallest scales, is built around the concept of a wave function that evolves in time according to the Schrödinger equation. The Schrödinger equation explicitly contains a time derivative. It describes how quantum states change as time progresses. The whole apparatus of quantum mechanics, the states, the observables, the probability amplitudes, presupposes a fixed background time against which quantum evolution can be defined. Time in quantum mechanics is not dynamic. It is external. It is the parameter with respect to which everything else changes. When physicists in the 1960s tried to write a quantum theory of gravity to apply the formalism of quantum mechanics to the geometry of spacetime described by general relativity, they encountered a consequence so strange that it has been called one of the deepest problems in all of physics. John Wheeler and Bryce DeWitt, working independently and then together, wrote down what should have been the fundamental quantum mechanical equation for the geometry of spacetime. And the equation they wrote, the Wheeler-DeWitt equation, has no time variable in it. Not a missing time variable, not a time variable that disappeared due to an approximation, no time variable at all. The equation that describes the quantum state of the universe, the most fundamental equation available for the cosmos as a whole, is timeless. The universe, according to the best attempt to write a quantum equation for it, is a static wave function on the space of all possible three-dimensional geometries. It does not evolve, it does not change, it simply is a static distribution of quantum amplitudes assigned to every possible configuration of the universe's geometry. This is the problem of time in quantum gravity, and it is not a minor technical puzzle that will be resolved when a graduate student adds a missing term to the equation. It is a conceptual confrontation with the possibility that time, as an external parameter, does not exist at the most fundamental level of physical description, that the flow of time, the past and the future, the arrow, is not built into the laws but emerges from the relationships between parts of a timeless whole. The way temperature emerges from the collective behavior of molecules that individually have no temperature. Julian Barber, whose Janus point we explored earlier, has been arguing for decades that this is correct. His book, The End of Time, published in 1999, laid out in detail the position that time is not fundamental, but is something that arises from the patterns of correlations in a static quantum state. In his view, the universe is not a process happening through time. It is a collection of configurations, each one a possible arrangement of all the matter in the universe, existing timelessly like the pages of a book that has already been written. What we experience as the flow of time is the experience of being embedded in a particular page of that book, one that contains within it the physical structures that we interpret as memories of other pages. The pages do not happen sequentially. They all exist simultaneously. The sequence is an illusion constructed by the information content of each configuration, which appears to point toward other configurations in a way that creates the impression of a temporal narrative. If this is right, then the question of whether time has one direction or two becomes the question of whether the static wave function of the universe has its amplitude distributed in a way that is symmetric or asymmetric under time reversal. The Wheeler-DeWitt equation, being time-symmetric, does not in itself favor one direction. Any solution to it that describes something resembling our universe should, by the symmetry of the equation, have a partner solution describing a time-reversed universe. The Janus point structure, in which two arrows of time emerge from a single moment of minimum complexity, is exactly what you would expect from a timeless wave function whose high-amplitude configurations include the complex, structured states that observers associate with memory and experience. The terrifying implication, the one that physicists in the field discuss among themselves and then often leave out of their public statements, is not merely that the universe has a second direction of time on the cosmological scale. It is that the direction of time you experience is being produced right now by your thermodynamic situation, by the specific configuration of entropy and correlations in your local environment, in a universe whose fundamental equations contain no preferred direction at all. The laws produced both arrows. You experience one, something else experiences the other, and the experience of one direction is not more real than the experience of the other. They are both consequences of the same equations, the same initial conditions, the same physics. The silence around this is not the silence of ignorance. The physicists working on the arrow of time, on the Janus point, on the CPT-symmetric universe, on the Wheeler-DeWitt equation, and the problem of time in quantum gravity are among the most rigorous and technically sophisticated researchers in the field. The silence is more like the silence after a deeply disorienting discovery, when you are not yet sure how to describe what you have found in language that does not mislead. It is the silence of people who know that what they have found is real, but have not yet figured out how to talk about it without the conversation running away from them. Because the moment you say, out loud, in a public forum, that time has a second direction, the implications begin cascading in ways that are very difficult to contain. People want to know if you can reach the other side. You cannot. The physics says you cannot. The expansion of space, the laws of causality, the CPT transformation that connects the two halves of the universe means there is no physical process that could carry you from our side to the mirror side or deliver any signal between them. They are causally disconnected, not just practically unreachable, fundamentally beyond any causal contact. The Big Bang singularity stands between them, a barrier made of infinite energy density. And on the other side, even if you could somehow reach it, you would be made of antimatter from the perspective of the matter you are made of now, and you would annihilate on contact with the first ordinary particle you encountered. People also want to know if the existence of a second arrow of time means that the future is determined, that everything is already written, that free will is a fiction. The block universe is sometimes interpreted this way, and the interpretation is understandable but not quite right. The block universe says that all times exist with equal reality as coordinates in the space-time manifold. It does not say that the future is determined. The future exists as coordinates, but the quantum mechanical nature of the processes that connect present to future means that those coordinates are determined by random quantum events that, in most interpretations of quantum mechanics, are genuinely indeterminate until they occur. The block universe and quantum indeterminacy are compatible. The future is there in the manifold, but which future it is depends on quantum events whose outcomes are not predetermined by any hidden variables that we know of. Free will, in whatever sense it is meaningful, is not obviously eliminated by a four-dimensional space-time. What is eliminated by the picture we have been building is a different thing. It is the cosmic privilege of the present, the sense that this moment, the one you are in right now, is special in a way that other moments are not, that it is real in a way that the past and future are not, that the direction of time flowing forward from where you are is the only genuine arrow. All of these intuitions are products of your thermodynamic situation. They are accurate descriptions of your local experience. They are not descriptions of the universe. The universe, as best physics can currently describe it, has no preferred direction of time at the most fundamental level. The laws are symmetric. The equations are symmetric. The quantum gravity description of the universe as a whole is timeless. The arrow of time emerges in your experience because you sit in a particular region of a low entropy universe that is evolving toward higher entropy configurations in one direction, and because your memory and perception record information in the direction that entropy points. On the other side of the Janus point, in the mirror universe that the CPT symmetry of the Big Bang implies, observers in the antimatter twin of our cosmos have the same experience. They feel their time flowing forward. They remember their past. They anticipate their future. They are as confident in the reality of their temporal direction as you are in yours. And both of you are right about your local situation, and both of you are wrong about there being only one arrow. This is not yet an experimental result. The mirror universe, the anti-universe, the Janus point twin, cannot be observed with any instrument that exists or that has been designed. The evidence for it is theoretical. It consists of the symmetry arguments, the CPT theorem, the Janus point models, the Wheeler-DeWitt equations, timelessness, and the experimental demonstrations that at the quantum level, time's arrow is reversible under the right conditions. None of these independently prove the existence of a second temporal direction. Together they build a case for taking the possibility very seriously. The experimental tests that might distinguish between cosmologies with one arrow and cosmologies with two arrows lie in subtle imprints on the cosmic microwave background. The CPT-symmetric model makes predictions about the spectrum of primordial gravitational waves that differ from inflation's predictions. It predicts a specific relationship between the masses of right-handed neutrinos and the density of dark matter that could, in principle, be tested by future particle physics experiments. If the neutrino mass predicted by Boyle, Finn and Turok, approximately 480 million billion electron volts, corresponds to a particle that can be produced and detected in a next-generation particle accelerator, that would be strong evidence for the CPT structure they describe. The Janus point model makes predictions about the growth of structure in the universe that differ in subtle ways from standard cosmological models. Future surveys mapping the large-scale distribution of galaxies with higher precision than currently available might find signatures consistent with one picture or the other. But even without direct experimental confirmation, the theoretical structure is what it is. The laws of physics are symmetric in time. The initial condition that gives time its arrow is unexplained by those laws. The equations that describe the universe at the quantum gravity level have no time in them at all. And every serious attempt to explain the arrow of time within the laws of physics, rather than simply assuming it as a boundary condition, produces a universe with two arrows rather than one. The second direction keeps emerging from the mathematics. It keeps showing up whether you approach the problem from Barber's Newtonian particle models, or from Turok's CPT cosmology, or from the time reversal experiments in quantum systems, or from the Wheeler-DeWitt equations' fundamental timelessness. The mathematics is consistent. The second direction is there. It is there in a sense that should now be clear, though it requires a precise statement to avoid misunderstanding. It is not there in the sense of being another timeline coexisting alongside ours in some parallel dimension. It is not there in the sense of being a second copy of history running simultaneously in some kind of adjacent reality. It is there in the sense that the mathematical structure of the universe permits, and according to some cosmologists requires, the existence of a second region of the cosmos governed by the same laws and the same physical processes as ours, but oriented in the opposite temporal direction relative to the point of minimal entropy from which both regions evolved. It is a second arrow that the universe produced naturally, that the laws of physics made inevitable, that our existence does not eliminate and our observations cannot directly reach. What is the experience of that second direction like? Here the physics must be honest about its limits. Physics describes the evolution of physical systems. It does not describe experience from the inside. The hard problem of consciousness, the question of why any physical process gives rise to subjective experience, is as unsolved in the mirror universe as in ours. If there are observers there, their experiences are, from their own perspective, exactly as vivid and immediate and real as yours. The forward direction they experience is as forward from their standpoint as your forward is from yours. The memories they have are as genuine to them as your memories are to you. Nothing about their situation tells them they are living in the backward direction. Nothing about your situation tells you they exist. This is what makes the second direction of time not just scientifically significant but philosophically vertiginous in a way that most cosmological facts are not. You cannot detect them, they cannot detect you. And yet, if the physics is right, they are there. There is one further layer to add, and it is perhaps the most disorienting of all, and the one that most directly earns the word terrifying in the title we started with, because we have been speaking of the second direction of time as something cosmological, something that exists on the other side of the Big Bang in the CPT mirror universe. But the same logic that produces the second direction at the cosmological scale produces it at every scale where the underlying laws are time-symmetric. The universe's laws do not distinguish the cosmic arrow from the local arrow. The laws that generate the second direction of time at the scale of the universe are the same laws that generate the second direction of time in the quantum systems, in IBM's quantum computers, and in the correlated quantum particles in Roberto Serra's Brazilian laboratory. The second direction does not appear only when you zoom out to cosmological scales. It is present, in a carefully qualified sense, at every scale where quantum correlations exist and where the second law is not being enforced by the sheer weight of astronomical numbers of uncorrelated particles. What this means for your experience of time right now is subtle but real. The memories you have of the past are encoded in physical structures in your brain. Those structures are quantum systems. The information in them is preserved, as quantum mechanics guarantees it must be, in the entanglement structure of the particles that constitute your neurons. The direction of time as you experience it is the direction in which those quantum states are accumulating correlations, building memories, increasing the complexity of your internal model of the world. And the direction in which that process runs is set by your thermodynamic situation, by the gradient of entropy in your local environment. But the underlying quantum mechanics knows nothing of that direction. The Wheeler-DeWitt equation applies to your brain as much as to the cosmos. The time symmetry of the memory kernel applies to your neural dynamics as much as to any other open quantum system. The second direction, from the perspective of the fundamental laws, is as available to the quantum systems in your brain as it is to the qubits in IBM's quantum computer. What prevents you from experiencing it is not a law, it is the overwhelming thermodynamic context in which your brain is embedded, a context shaped by the enormous entropy gradient that stretches from the ordered early universe to the disordered far future, a gradient so vast and so powerful that no local reversal of time's arrow can survive contact with it for more than an infinitesimally brief period. You are, in this picture, a kind of information processing system that is experiencing one of two equally fundamental temporal directions because of where you sit on the entropy landscape of a particular universe, not because the universe has only one direction built into its laws. The direction you call forward is the direction your thermodynamic situation enforces, not the direction the laws prescribe. The laws prescribe nothing. They permit everything. The universe ran both directions simultaneously. You are in one of them. And this is why the silence of physicists on this topic is not ignorance. It is the silence of people who have thought about what follows from saying this out loud, because once you accept it, the next question is unavoidable. If the direction of time is not a law, but a consequence of thermodynamic context, and if the thermodynamic context is set by the initial condition of the universe, and if the initial condition of the universe is the improbably ordered state that Roger Penrose calculated has a probability of 1 in 10 to the power of 10 to the power of 123, then the direction of time you experience is the consequence of a condition that is itself essentially miraculous in its improbability. You are experiencing the forward direction of time because you live in the aftermath of an extraordinarily unlikely initial condition. The fact that you live in the aftermath of that condition is, of course, not mysterious in the anthropic sense. If the initial condition had not been extraordinarily ordered, you would not be here to find it remarkable. The universe would not have produced stars or planets or chemistry or biology. You exist precisely because the initial condition was what it was. This does not explain the initial condition, it merely notes that your existence is correlated with it. But the existence of the second direction of time, the one that the mathematics keeps producing, whether or not any observer is there to experience it, is a different matter. It is not anthropically constrained. The mirror universe's second arrow of time does not depend on the presence of observers. It is a structural feature of the universe's mathematics, present whether or not any complex system arises to record or experience it. And the fact that the mathematics requires it, while the physics community has been reluctant to discuss it, is the quiet intellectual tension at the heart of everything we have covered tonight. What the evidence from thermodynamics, from particle physics, from quantum experiments, from the Janus point model, from the CPT-symmetric universe, and from the Wheeler-DeWitt equation collectively suggests is that the universe has always had two directions of time. The second one has been there in the mathematics since the laws were first written down. It appears in every framework that is honest enough to include it. It shows up in laboratory experiments at the quantum level. It is produced by the same initial conditions that produced the first. The reason it was not discussed was not that it was not there. It was that discussing it forces a confrontation with implications that physics as a discipline has not yet found the right language for. The right language would have to be able to say, without the statement being misunderstood as science fiction or mysticism, that the universe has two temporal directions running simultaneously from a single initial point, that observers experience one direction because of where they sit on the entropy landscape, that the direction they do not experience is as real as the one they do, and that the laws of physics made this inevitable. It would have to be able to say that the flow of time you feel right now, the sense of this moment being real in a way the past and future are not, is not a law of nature. It is a consequence of thermodynamics. It is as fundamental to your experience as breathing and as contingent on your physical circumstances as your temperature. It would have to say that another direction of time is running right now, has been running since the Big Bang, is built into the equations, has been measured in quantum labs, emerges from every theoretical framework that approaches the problem without prejudice, and that the fact that you cannot feel it, cannot reach it, cannot in any way detect it, does not make it less real. It makes it the most real thing about reality that you cannot experience. That is what the silence has been protecting, not a secret, a recognition accumulated slowly and carefully by the physicists who think most seriously about time, that the universe is more symmetric than the universe allows itself to appear from any particular observer's vantage point, that the one direction of time you experience is your local slice of a much larger, much more symmetric, fundamentally directionless cosmos, that the second direction is there in the mathematics, in the experiments, in the symmetry of the laws, in the CPT twin of our universe, in the Janus point from which two arrows diverge rather than one. What do you do with that? Not in the laboratory, not in the equations, in the ordinary human sense of what to do with a fact that is simultaneously verifiable and impossible to experience directly. This is the question that brings the physics back to the human scale, and it is, in a sense, the question the field has been avoiding by staying quiet. You do what you do with every fact about the universe that is real and unreachable. You let it change the shape of what you think is true without letting it paralyze the experience of what you feel is true. The experience of time flowing forward is real. It is the product of real physics applied to a real thermodynamic situation. The fact that this experience is generated by conditions rather than laws does not make it less genuine as an experience. It makes it more interesting. It makes it the local expression of a cosmic symmetry that is far larger than any observer. It makes the act of remembering and anticipating and deciding and experiencing not less meaningful because it is thermodynamic, but more remarkable because it is thermodynamic, Because out of a universe whose most fundamental equations contain no time and no preferred direction, the conditions of the early universe produced a gradient so powerful and so organized that it generated the experience of time flowing forward in a mind made of matter. And on the other side, the same conditions, by the same laws, generated the same experience in a mind made of antimatter, running in the other direction, equally certain of its own temporal reality, equally embedded in a cosmos whose equations, read honestly, give it no privilege over the direction it calls backward. Einstein was weeks from his own death when he wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. He was not being glib, he was applying his own theory to the fact of Michel Besso's death and finding in that application a form of honesty about what time actually is at the level where physics has anything real to say about it. The illusion he named was not the experience of time. The experience is real and irreducible. The illusion was the specialness of the present, the absolute reality of the forward direction, the sense that this moment and no other is the real one. This, the physics says, is what the brain constructs in the context of a thermodynamic gradient. And this is what any sufficiently complex information processor embedded in a low-entropy universe would construct. This is what the equations produce when you apply them not just to the cosmos, but to the smaller systems within it that are capable of recording and experiencing. The second direction of time is real. The physics is clear about this and has been becoming clearer every decade since Boltzmann wrote down his equation and noticed, with something between triumph and horror, that it implied the second law was statistical rather than fundamental. The equations know nothing of one direction. The experiments are beginning to demonstrate the reversibility of the arrow at the quantum level. The cosmological models that take the symmetry of the laws seriously produce a universe with two arrows. The CPT theorem requires, if its constraints are applied to the universe as a whole, a mirror of our universe on the other side of the Big Bang in which time runs the other way. None of this is hidden. The papers are published, the experiments are reported, the mathematics is checked and rechecked. What has been missing is not the evidence. What has been missing is the willingness to say, in language that does not soften the conclusion, that time has always had a second direction, that the physics has always known this, that the experiments are confirming it, and that the universe has been running both directions simultaneously since the first moment, waiting for someone to say so. The universe does not tick in only one direction. The universe does not prefer forward over backward, future over past, the direction you call time flowing over the direction you call the past. It produces both. It has produced both since the Janus point. The experience of one is what you get when you are embedded in one. The existence of the other is what the equations say is true. Neither cancels the other. Neither makes the other less real. Both emerge from the same physics, the same initial conditions, the same fundamental laws that your GPS uses and your quantum computers run on, and your coffee obeys when it cools. You are sitting inside one of the universe's two temporal directions. The other one is running alongside yours, in the only sense that alongside means anything when one direction runs backward to the other, coexisting in the same mathematical structure, governed by the same laws, unreachable, undetectable, and as certain as anything physics has ever found. The terrifying part is not that it exists. The terrifying part is that the equations have been saying so for 150 years, and everyone kept hoping they were wrong. They were not wrong. The universe is more symmetric than it looks. Time has a second direction. It has always had one. The silence is over. Sleep well, knowing that whatever this moment is, the laws that produced it produced another moment simultaneously in another direction that knows nothing of your existence and is as certain of its own forward direction as you are of yours. The universe kept both. It always does. It always will.